Welcome to this installment of the Secure Your DNS, Secure Your Network series. My name is Tim Rooney, Director of Product Management at BT Diamond IP, and the goal of this video series is to break down into bite-sized chunks the many ways that the domain name system, or DNS, can be attacked or manipulated for nefarious purposes, and mechanisms that you can put in place to shore up your defenses to better secure your DNS and therefore better secure your network. In this video, we'll talk about DNSSEC once again, the DNS security extensions, and this is part 2 that deals with administration of DNSSEC from a DNS zone administrator's perspective. Part 1 looked at the resolution process. What does DNSSEC do to protect your DNS information and your resolution process? Now, DNSSEC relies on digital signatures. So each zone is typically signed with 2 private keys. So the way digital signatures work, let's just look at one key, for example. You create a private key that is used to actually sign your information. You take, let's say, a resource records set, which is a set of resource records of the same owner, field, type, and class. So let's say www, internet class, and a type, which is for an IPv4 address. So you would group all those records together, sign them as a whole, and create one signature in the form of an RR-SIG record. And that is your signature, and I'm creating that signature using the information in the RR set, but also using the private key for that zone. Now, what I publish in the zone is the public key that can be used to basically validate that signature. And the validation of that signature basically states that that information that I received back is indeed signed by that key, the private key corresponding to that public key, and that that information has not been manipulated between the time the server that I asked for it from and the time I got it back to my resolver, my validating resolver. So it provides that origin authentication as well as data integrity validation. And then DNSSEC also provides the authenticated denial of existence for records that don't exist. Now, in the case of DNSSEC, we're using 2 pairs of keys. So we've got a zone signing key, signs the zone data, and this is a smaller key. It's a little more computationally simple for the signature validation process, just from a performance perspective. It can be changed more rapidly. It's self-contained, as we'll talk about in a moment, and for that reason, it can be changed more frequently, just like you change your passwords. So the zone signing key signs the data in the zone, the resource records, and then the key signing key, the KSK, signs the DNS key RR set. And the DNS key is basically the statement of the public keys of the zone. The zone signing key, public key, and the key signing key, public key, is literally published in the zone in the form of these DNS key records. It's signed by the KSK, and that is a longer key, a little more computationally expensive, and it can actually last longer because it's harder to crack. But it also links in with the chain of trust that we talked about in video 1 to the parent zone in the form of the KSK hash existing in the delegation signer record. So the KSK is used to link in the chain of trust. Ultimately, up to the root zone, it serves as the trust anchor so that a recursive server can validate the key and validate all the signatures down to the resolution information in question. So that's, in a nutshell, why you have the zone signing key and the key signing key. Both keys, public keys, are stored in the DNS key resource record set within the zone, and the corresponding private keys should be stored securely, even with a hardware security module if appropriate, so that an attacker can't compromise and get your private key. So they can get your private key, they can basically come up with alternative zone information to mimic your zone, sign it with your key, and it'll look legitimate. So you want to keep that private key secure. Signatures are stored within the RR-SIG record type, as I mentioned, and each RR set is signed. So again, that's RR resource records of the common owner, class, and type. And they're grouped together canonically in the zone, signed as sets throughout the zone. And then the signatures, RR-SIG signatures, also contain signature inception and expiration times. So these are expressed as absolute times, so there is a timing component that has to be kept in sync to make sure that that signature validation is existing with respect to the expiration. Authenticated denial of existence, I mentioned, this is performed through the NSEC, NextSecure, NSEC, and NSEC3 record types, as we discussed in video 1. So the recipient or the validating resolver validates the data in the resolution itself based on the information it asked for, getting the information back, and then looking at the signature on that information, basically using the public key to validate the signature on the information. And if that matches, that basically validates the resolution process. And then it follows that up the chain of trust to the root zone, as we discussed in video 1. So the basic implementation for your caching server. So again, this is the server that's making the query, getting the answer back, and validating the signatures. So you want to start with the trust anchors, as we talked about with the chain of trust going up to the root zone. You need that root zone public key in order to perform that chain of trust validation. You can put that into your recursive server configuration. With ISC bind, for example, you can use a trusted keys statement within your named.com file, or a managed keys, which managed keys actually follows along with the internet. It queries the root periodically to be able to update with changes. There's a first internet key rollover occurring on October 13th, 2018, and if you've got the managed key set up, it should automatically keep up and roll that key right along with the root. So the update of the trust anchor on key rollover is not manually necessary if you're using the managed key statement, and that process of the trust anchor management is defined in RFC 5011. So you configure the managed keys for your trust anchors. A lot of the implementations, recursive implementations today, have that pre-configured for you. You just want to make sure you've got the correct trust anchor there, given the rollover at this point. But they roll every couple of years, so it should be valid if you've got a recent vintage implementation. And then there's perhaps other DNSSEC parameters or policies you can define on your recursive server with respect to requiring DNSSEC validation or not. You want to pass it to your clients if it's not signed, or if it's not valid, or the signature is expired. There's also a negative trust anchor component that if you are validating DNSSEC and there's a domain out there where perhaps the administrator is new to DNSSEC, they're not doing it right, the keys aren't validating, you can actually denote it as a negative trust anchor to say, well, skip that domain for now. You want to notify that domain administrator to make sure that they hopefully figure things out quickly, get that working, and hopefully it wasn't a compromise. But you can use that as a stopgap to turn off validation for that trust anchor, or that component of the tree, until they get the situation rectified. A DNSSEC look-aside was a mechanism used to set up kind of an alternative route from a DNSSEC perspective, but that's been decommissioned now that the route has been signed for quite some time. And then there's implications on other technologies in DNS that basically manipulate the answer that's provided by the authoritative name server. So the whole premise of DNSSEC is to authenticate the information as signed by the domain administrator and to validate the data integrity back to the resolver. But with DNS64, as well as response policy zones, there's an implication there that I'm modifying the answer I get back before I pass it back to my stub resolver, and thereby invalidating the signatures, because that's the very thing that DNSSEC will detect, is any modification of the data. So it's really just a trade-off with respect to handling DNSSEC and these other technologies, and just something to keep in mind as you set up your policies on your recursive servers. Now, that's all there is to it on the recursive side. On the authoritative side, this is where you're signing the zone information. You publish, let's say, external DNS information, and you want to publish that. We briefly talked about this in the highlights of how it works in the prior video, but basically you want to generate key pairs. There's actually a pair of pairs, as I mentioned, a private and public component. The key signing key, the zone signing key, again, the utilities are generally provided by your DNS implementation. You want to add the public keys to the zone file. You can use an include statement or just paste them in. And then you want to then sign the zone. So again, there's utilities for that generally. And what happens there is that the signing process canonically orders the information, basically, in essence, alphabetizes it, but that's really an oversimplification, but you can think of it as something like that, where it's canonically ordering the zone, basically insert your NSEC or NSEC3 records, which are next secure record for the authenticated denial of existence, the NSEC being the plain text version, so to speak, the name explicitly mentioned, whereas the NSEC3 hashes the owner name of the next record. And then the signing process, of course, calculates the RR sig, the signature, on that resource record set and also publishes that in the zone. To link in with the chain of trust now, you need to notify your parent zone administrator, who hopefully is also signed to make this valid, of your key signing key. Again, this is the longer key, not changed as often, but your parent zone administrator needs to have a copy of your KSK in order to define a delegation signer record that they can sign in their zone, thereby linking you into the chain of trust, and hopefully they go up to the root. Thereby, those validating resolvers can validate your signatures up to your parent zone all the way up to the root. So every once in a while, though, like passwords, you do need to change your keys, or what we call roll keys, roll them over, which means it's not a flash cut, but a way to publish multiple keys at once. So then we'll talk about why you need to do this as well a little bit later. But basically with the ZSK, it's all self-contained within the zone. You generate the key pair for the ZSK, add the key to the zone, and then re-sign the zone. There's no need to communicate with an external party such as the parent zone administrator, because you're just changing the ZSK, which your current KSK signs, therefore keeps it linked in with the chain of trust. However, when you do roll the KSK, and again, these are longer keys that exist for longer periods of time, so that you don't have to perform this process quite as often, but in this case, you have to go through really the whole process again. Creating the KSK pair, publishing, including the public portion in the zone file within the DNS key resource record set, signing the zone, and then also distributing your KSK up to the parent zone administrator to be able to link again to the chain of trust. So you've got the key management process with respect to managing your authoritative servers for DNSSEC, creation, publication, activation of the key, rolling over the key, the zone signing itself. Typically, all the implementations provide ways to do this automatically, so hopefully that is not too onerous. But every zone has to be signed, so if you've got hundreds of zones, each one needs its own set of keys and signatures, signature processes. You've got the parent zone updates with the KSK. Every time you change your KSK, you need to notify the parent zone. And if you are running a trust anchor, which hopefully you aren't, because again, this is just all these recursive resolvers out there are trusting, if they're trusting your key, you need to notify them of any changes, of course. But hopefully you're just linked in with the chain of trust up to the root, and it's just the root zone change that needs to be updated in your recursive resolvers. The maintenance is basically keeping signatures updated. So again, signatures have an inception and expiration time, so information needs to be re-signed periodically, and so that also is typically done on a automated basis by major implementations of DNSSEC. And then you've got the roll process, as we just alluded to here, because you've got a process where you've got caching going on in the DNS architecture. There needs to be a process of really publishing information in multiple cases. So let's take a closer look at why you need that. So let's say I've got an example.com zone here on my authoritative master. I'm using a key here, and I'm creating the signatures. I'm publishing this key in my zone so that the information can be validated by those who receive that. And let's say I've got some slave servers here, or secondaries, to which I pass that information as well. Now let's say somebody asks for example.com, and that recursive server gets the information back from that zone, the authoritative server, one of the slaves, for example, and it provides that, it stores that key information so that other queries for information within example.com can also be validated, but with the same public key. So because all the resource record sets within that zone are signed with the same private key, I can validate them all with the same public key. And likewise, from the stub resolver perspective, in cases where it's caching information, it would also store that cache for the same reasons of validating. If you're doing stub resolver validation, which in this case is a validating resolver, and some browsers support this natively. In the typical case, your recursive server will do the validation for the stub resolver, but in this example, let's just assume it goes all the way out to the edge to provide full end-to-end authentication and data integrity checking. So let's say now my authoritative zone, I need to change my zone signing key, let's say. So I update my master and zone transfers to my secondaries. Meanwhile, I've still got a copy of the old public key in my caching servers and perhaps even in my resolver. So I'm able to, as I query for other elements in the example.com zone, I'm going to try to authenticate or validate them using this old key. And if I just do a flash cut with this new key, that's not going to validate, because the signatures are signed with the new key, and the information I'm getting back is based on that new key, and so it's not going to validate with the old key. So for this reason, I need to have some lingering of that old key for a while to make sure that it's still valid within that zone to validate those signatures. And then likewise, as other stub resolvers are querying this caching server, again, because that information is cached, it's going to just say, well, here I've got the public key of that zone in the form of the DNS key record. The TTL has not expired yet, it's still valid, and therefore you can validate based on that. So again, you might have a mismatch if there's other information. If you've asked for www in the past and that's been validated and signed, that could be validated and passed along natively. However, if you're asking for mail.example.com, you get a new resolution answer. That signature may not match because it's, again, signed with the new key, not the old key. So ultimately, when that cache expires on the recursive server, it will then get the new DNS key record in the zone and be able to perform the validations. But really, for this reason, there is a state where you've got multiple keys out there for the zone, and therefore with zone signing keys, there's typically a pre-publish situation where you've got multiple keys that are published in a zone. Therefore, my recursive server and even my stub resolvers can cache both keys and attempt to validate using the first key, the old key. If that doesn't work, try the new key. And in that situation, I'm able to then validate the information back using one of the keys that the zone administrator has signed there as legitimate. So that's why we call it a rollover. It can't be a flash cut process. There's a situation or a time frame where both keys need to exist for both the KSK and the ZSK. So in terms of deployment considerations, so one thing to consider, implementation and maintenance complexity or not. I think back in the early days of DNSSEC, it was very complex, it was very onerous, very manual. A lot of pretty much all the major DNS vendors have implemented automation there, both on the recursive side, thanks to RFC 5011, where you can basically have your recursive resolver update the root zone key as it rolls and automatically update that so that you don't need to manually implement any steps there to keep the keys up to date for validation. On the authoritative side, again, there's a lot of automation capabilities built in where new keys can be generated, new signatures created, rollover processes automated, and so forth. So a lot of that too has been automated by major vendors, and so it is really not as complex as it once was. So if you haven't looked at DNSSEC implementations in a while, I invite you to do so. DNS response packet size, because of the signature records, the RR-SIGs, you know, if you've seen a digital signature or certificate, for example, it's got a lot of characters there that look like random characters, but that's basically the signature in a text format, and so this adds to the payload of the answer you're getting back, and this is a consideration, small price to pay in terms of the security it provides, but there's always a trade-off. Zone file size, really for the same reason. Query performance impact, there may be additional queries required, but typically, again, these keys and DS records are really provided on the way down the tree as you're going from the root to .com to example.com, so there's really not an additional query, but that information is cached as well. Stolen key contingency plan. This is just something to keep in mind should your key be compromised. As I mentioned, if somebody does get a hold of your private keys, they can sign arbitrary data and make it look legit. Should you discover that situation, you need to change your keys immediately. And so just making sure you've got a plan mapped out to do that, to publish the new key, revoke the old one, and get that information out there. Time synchronization, as I mentioned, signature RR-SIG records have an inception and expiration time. So, using NTP, network time protocol. Dynamic update, so if you're making changes to your zones, You need to re-sign them because of you need to add more of these NSEC records. Let's say if I'm adding a record between two that my NSEC had formerly skipped over, you need to reinsert that, sign it, add the corresponding NSEC or NSEC3 records. So from a dynamic update perspective, you want to certainly secure your dynamic updates because you're securing your zone information. You want to make sure the process of getting data into the zone is secure as well, so you can implement update policies to do that, transaction signatures, etc. And then just to make sure that information coming into the zone is legit authenticated before it's further authenticated by the zone itself through the DNSSEC signing process. In consideration of using NSEC versus NSEC3, it's really just a trade-off between easy footprinting versus computational costs. If you've only got a few external records out there, www, mail, kind of the standard ones that at least a lot of the organizations publish, it may not be a big deal to offer footprinting because it's kind of commonplace anyway. But again, it's a trade-off to consider in your organization. And then lastly, DNSSEC is effective against cache poisoning, but not intended as a comprehensive security solution. So there are many ways to attack DNS, which is really the very reason for this video series. But DNSSEC is not a panacea for all of DNS security. It certainly is very effective for helping to authenticate DNS resolution information as authenticated by the zone administrator and to validate the data has not been manipulated while traversing to your validating resolver. So DNSSEC is effective for what it does, but it's one ingredient in your overall DNS security strategy.